Hello everyone and welcome back. In this video we're going to start inferential statistics, which is making conclusions about populations based on sample data. Whenever we are given certain types of sample data to analyze, there will generally be two types of methods that we will discuss. Now, one method deals with estimating the parameter of interest, which are called confidence intervals, and the other method deals with making a decision about two competing claims about the parameter of interest, which are called hypothesis tests. For this chapter, we will focus on inferences for categorical data, and we will begin with finding confidence intervals for a proportion. Now recall that under certain assumptions and conditions, the sampling distribution of the proportion will be approximately normal, with the mean equal to p, and the standard deviation equal to the square root of p times 1 minus p all over n. Now there is a problem with using this model. We typically don't know what the true population proportion is, so we take a simple random sample and estimate it with a sample proportion. Whenever we use a single number to estimate a parameter, then this is called a point estimate. For example, the sample proportion p hat is a point estimate for the population proportion p, and the sample mean y bar is a point estimate for the population mean mu. Now, because p is needed to calculate the standard deviation of the sampling distribution, we will also need to estimate it with the sample proportion. When we estimate the standard deviation of the sampling distribution, then we call it a standard error, and we denote it with SE of p hat. So the standard error for the sample proportion is the square root of p hat times 1 minus p hat all over n. So we replace the population proportion with our sample proportion p hat. So how can we use the sample proportion and the standard error? Well, we know that for normal distributions, that about 95% of values will fall within two standard deviations of the mean. But since we don't know what p is, we will estimate it with p hat. And let's suppose it's this value over here. Now let's change our perspective. If we were to extend two standard errors above and below this sample proportion, then we hope that this interval will capture the true population proportion. And so we can use an interval estimate to provide an interval that contains the population proportion p with a confidence level. And this interval is called confidence intervals. Generally, these intervals will take on the form where we have our point estimate plus or minus ME. And ME stands for the margin of error. Now, the margin of error is a way of describing our uncertainty in estimating the population parameter. And it is typically the product of a critical value and a standard error from the data. So when we're calculating a confidence interval for a proportion, the margin of error is given by Z star times the standard error. And Z star is called the critical value. Now the critical value is the number of standard errors to move away from the mean of the sampling distribution to correspond to a specified level of confidence. So for example, in the standard normal model, we denote our critical value by Z star. And for a 95% confidence level, the critical value Z star is equal to 1.96 because 95% of values will fall within 1.96 standard deviations of the mean. So let's take a look at other examples of calculating these critical values. So let's find the critical value which corresponds to a 99% confidence level. So for 99% confidence, the central area under the standard normal distribution is going to be 99%. So the area of the central region is 0.99. And so in order to determine the critical value Z star, we need to determine the area to the left of Z star. So if the central area is 0.99, that means the remaining 0.01 area are in both of the tails. And because of symmetry, the area of the left tail is going to be half of 0.01, which is 0.005. And so the total area to the left of Z star is 0.99 plus 0.005, which gives 0.995. So now we want to look inside of the Z table for the two closest values to 0.995. So the two closest values are 0.9949 and 0.9951. So the area to the left of 2.57 is equal to 0.9949, and the area to the left of 2.58 is 0.9951. Notice that 0.995 falls right in between these two areas, so the critical value will be the average of the two Z scores. So Z star is going to be 2.57 plus 2.58 all over 2. And so the critical value for 99% confidence is 2.575. So now let's look for the critical value that corresponds to an 80% confidence level. So for 80% confidence, you want to find the Z score which corresponds to the central 80% of data. So the area of the central region is going to be 80%, or 0.8. And in order to find Z star, we need to know the area to the left of Z star. If the central area is 0.8, then the remaining 0.2 area must be in both tails. And because of symmetry, we know that half of 0.2 are in both of the tails. So the area in the left tail is 0.1, and the area in the right tail is also 0.1. And so the total area to the left of Z star is 0.9. So we want to look for the two closest values to 0.9 inside of the Z table. So looking up the two closest values in the table gives us 0.8997 and 0.9015. So the area to the left of 1.28 is 0.8997, and the area to the left of 1.29 is 0.9015. So notice that 0.9 is closer to 0.8997 than it is to 0.9015. And so we'll choose the closer value, which is 0.8997. And so the critical value is 1.28. So now we're ready to find a confidence interval for a proportion. Now this interval is called a one proportion Z interval and is named this way since we're looking for a confidence interval for a single proportion using the normal model. Now since we want to use the normal model for the sampling distribution, then we must meet certain assumptions and conditions. And these are the same as what we have seen in the previous chapter, and so we repeat these here for your convenience. So recall that we have the independence assumption, and we check the two related conditions, which are randomization and the 10% condition. And the other assumption is the sample size assumption. And we can check the corresponding condition, which is the success and failure condition. Now, once these conditions are met, then we can calculate the confidence interval as p hat plus or minus the margin of error. And the margin of error is given by the critical value Z star times the standard error. So now let's look at an example. Consider tossing a coin 100 times and the results show 39 heads. Based on this result, what interval captures the most likely 95% of the values for the true proportion of heads? And does this interval suggest that this coin is fair? So here we're looking for a 95% confidence interval. So the first thing we need is the estimate. So the sample proportion p hat is the proportion of heads in our sample. So we observed 39 heads out of 100, and so p hat will be 39 divided by 100, which is 0.39. So the next thing that we need is our critical value, which is given by Z star. And here I've listed a table of commonly used confidence levels with their critical values when we're calculating a Z interval. So our confidence level is 95%, and so the critical value is 1.96. Now the last thing that we need is the standard error. So our sample size is 100, and the standard error is given by the square root of p hat times 1 minus p hat, all divided by n. And so this is the square root of 0.39 times 1 minus 0.39, all divided by 100. And this will be approximately 0.04877, and so on. And so now we're ready to calculate our confidence interval. Which is given by p hat plus or minus Z star times the standard error. So we have 0.39 plus or minus our critical value, which is 1.96, times our standard error, which is 0.04877. And this will be equal to 0.39 plus or minus a margin of error of 0.04877. 0.09559. And so if we take 0.39 minus the margin of error, we get 0.294. And if we take 0.39 and add the margin of error, we get 0.486. Now, whenever we construct a confidence interval, then we typically write a statement about our findings. And so what we can say is that we are 95% confident that the true proportion of heads falls between 0.294 and 0.486. Now, this does not mean that there is a 95% chance that the true proportion of heads is between 0.294 and 0.486. So the 95% confidence is not a probability. And so we will look at how to interpret these types of confidence intervals in the next section. Now, does our confidence interval suggest that this coin is fair? Well, if the coin was fair, then the true proportion of heads would be equal to 0.5. But notice that 0.5 does not fall within our confidence interval. So since 0.5 does not fall within our confidence interval, then this suggests that this coin is not fair. So this will conclude our lesson for this video. In the next video, we will talk about the correct interpretation of confidence intervals, and we will go over some more examples of finding these confidence intervals. And I'll see you then.